Usually, we do not know the prior probabilities and/or the class conditional densities. Therefore, linear and quadratic discriminant analysis, kernel discriminant analysis, and k-nearest neighbors are approaches that can be applied. All three methods approximate Bayes' decision rule using the learning sample to get estimates of the posterior probabilities. Linear and quadratic discriminant analysis assume the form of the underlying density is known to be multivariate normal. Note, the discriminant function may be more conveniently expressed by taking the log, such that the products of these terms becomes a sum. Here, we have simply plugged in the multivariable normal density for class K. Because there are p predictors, x is a p-component column vector, mu is a p-component mean vector, sigma is a p times p variance-covariance matrix, and -1 indicates the inverse, and this indicates the determinant. Therefore, linear and quadratic discriminant analysis are parametric. That is, the methods assume that the forms for the underlying density function are known. In the special case where the features are statistically independent and each feature has the same variance, sigma squared, the two middle terms are not dependent upon class, so they are unimportant constant terms that can be omitted. Effectively, to classify a new observation, you simply calculate the Euclidean distance from the observation to each of the k-mean vectors and assign it to the class having the nearest mean. So this is a minimum distance classifier. For this special case where we assume that the classes have a common variance-covariance matrix for all classes, again, the two middle terms are not dependent upon class, and so they are unimportant constant terms that can be omitted. In the second special case, to classify a new observation, you simply calculate Mahalanobis distance from the observation to each of the k-mean vectors and assign it to the class having the nearest mean. For this special case where each class has its own unique variance-covariance matrix, only the second term is a constant term that can be omitted. Therefore, the decision boundary between two classes is described by a quadratic equation. In all three cases, if the prior probabilities are the same for all classes, the last term can be ignored. In practice, we do not know the parameters of the Gaussian distribution, and so we estimate them using our training data. The mass R package includes the function LDA for linear discriminant analysis. Applying the LDA function to our data frame simulated that includes two predictors, x1 and x2, and the binary outcome y, we use the familiar y is modeled by the sum of the predictors where we indicate the name of our data frame. The resulting object is a list that includes several components. Printing the object reveals estimates of the prior probabilities and mean vectors. Applying the predict function yields the predicted class as well as the posterior probabilities. The mass R package also includes the QDA function for quadratic discriminant analysis. On the left is a scatter plot of the two predictor variables where x2 is plotted against x1 for our simulated data frame, where a different color is used to indicate the observed class y. On the right is the same plot where now the color used is to indicate the predicted class from our LDA function. It is easy to visualize the linear decision boundary, which is why this technique is linear discriminant analysis. An interesting feature of LDA is that when the classes are well separated, the parameter estimates for the logistic regression model are surprisingly unstable. However, linear discriminant analysis does not suffer from this problem. Kernel discriminant analysis does not assume a parametric class conditional density, but rather estimates the class conditional densities nonparametrically by applying a kernel function and a smoothing parameter to the histogram. Consider the form of the kth discriminant. Kernel density estimation is used to estimate the class conditional density, which is then plugged in to estimate the posterior probabilities. That is, kernel discriminant analysis substitutes the nonparametric estimates of the class conditional densities derived using kernel estimates into Bayes' decision rule. The R package KS includes a function, KDA, for performing kernel discriminant analysis. This function does not take a model formula, but rather the first argument is the matrix of predictor variables and the second argument is the class. A plot of the predictions demonstrates that the nonparametric densities yield an irregular shape, which may be helpful for predicting class. In fact, when tabling the observed versus predicted class from kernel discriminant analysis for the training data, it outperforms linear discriminant analysis. We should be cautious though, as these error estimates are based on the training data, so they are resubstitution error estimates and are known to be biased. Both linear discriminant analysis and quadratic discriminant analysis assume a multivariate normal distribution for the class conditional densities, while kernel discriminant analysis estimates the class conditional densities nonparametrically. For high-dimensional covariate spaces, kernel estimation breaks down because points are no longer close, so that each estimate will be based on only a few observations. Rather than using a multivariate kernel estimate, we can make a simplifying assumption that for a given class, K, the P features are independent. Therefore, the P-dimensional class conditional density can be estimated by the product of the individual P densities. On the other hand, K nearest neighbors does not attempt to estimate the class conditional densities, but rather estimates the posterior probabilities directly. Thinking about an individual observation, we grow a region about that observation until K sub n observations are identified, where K sub n is some specific function of n, our sample size, which is usually some predefined constant, such as the square root of n. When applying K nearest neighbors, first, for each observation, form the class-specific indicator variables, such that the jth indicator variable is 1 if observation I is in class J and 0 otherwise. Then, for a given observation that needs to be classified, rank the distance from all observations to that observation of interest in increasing order, using some metric distance, such as Euclidean distance, and denote the ranks by r sub 1 to r sub n. And also select an integer k sub n. For each observation, define the weight associated with the observation to be classified. The weights are 1 if the rank distance is less than or equal to k sub n and 0 otherwise. The estimate of the posterior probability for class J is given by this equation, which is simply summing the number of nearest neighbors in class J and dividing by the number of the nearest neighbors. Then, Bayes' decision rule to predict class is simply the argument that maximizes the posterior probability. As an example, suppose we have 5 observations and we want to classify the third observation using k sub n equals 3 nearest neighbors. Using the observed class, which is 1, 2, or 3, we also set up our 3 class-specific indicator variables, such that the jth indicator variable is 1 if observation I is in class J and 0 otherwise. X sub 1 and X sub 2 are the predictors which were measured for each observation. Using these predictors, we calculate the distance from each observation to observation 3, our point of interest. We then rank the distances in increasing order. Because we are using k sub n equals 3 to capture the 3 nearest neighbors to our point of interest, the weights are 1 if the rank distance is less than or equal to k sub n and 0 otherwise. The estimated posterior probabilities are given here, and we see that class 2 is the argument that maximizes the posterior probability, so we predict observation 3 is in class 2. The R package class implements k nearest neighbors in the KNN function. Because the k nearest neighbors classifier predicts the class of a given test observation by identifying the observations that are nearest to it, the scale of the variables matter. Any variables that are on a large scale will have a much larger effect on the distance between the observations, and hence will drive the classification result. A good way to handle this problem is to standardize each feature to have a mean 0 and a variance of 1, since it is often the case that features are measured in different units. The k-nearest neighbor function does not take the model formula, but instead takes a trained data set for model training and a test data set, which is for class prediction, and class, which is a vector indicating class membership for the training data set. The number of nearest neighbors is specified. Because we may want to look at the predictions for the training data to compare to linear discriminant analysis and kernel discriminant analysis, we simply pass the same data for both the train and the test arguments. The predictive performance is better than linear discriminant analysis and comparable to kernel discriminant analysis. Some additional notes. One of the most important steps in choosing a metric may be to exclude features which have no or little relevance. Kernel density and k-nearest neighbors methods make minimal assumptions about the form of the underlying distribution. There are some limitations to these methods. First, these methods are sensitive to the choice of the metric, and no specific metric distance is preferred. Second, there is no natural or simple way to handle categorical variables and missing data. Some solutions exist, but software seems to be lacking. Third, these are computationally expensive classifiers. The full training set must be stored so that the interpoint distances can be calculated for each new observation to be classified. Finally, these methods give very little usable information regarding the structure of the data. That is, they lack power of explanation for the predictor variables.